Welcome back everyone. In this lesson we are going to try out open methods of finding roots of equations. In the last few lessons we have learned about bracketing methods, which are the bisection methods and the false position method. Later we also covered the incremental search procedure, how to initially set the boundary points for bracketing methods as well as open methods. And from these lessons we are going to try out the open methods. We are going to learn these methods. So among the open methods, we will first cover the simple fixed point iteration method. So let's dive into the details of these methods. So there are some differences between bracketing methods and open methods. In bracketing methods, we had to initially define two boundary points, and we were pretty much sure that within the boundary points there should have been at least a single root. So that's the difference where the open methods plays. In the open method, we need to specify just a single starting point, a single boundary point. Although we should not call it a boundary because it seems a single point. So unlike the bracketing methods, in open methods, we just specify only one single starting point. So that's why it is called an open method. There is no bounding segment, or there is no boundary. That's why it is called an open method. But since it is an open method and it requires only single starting point, it seems very much useful and very much easier than the bracketing method, because we do not need to specify any boundary locations and we do not need to be sure that there is any root situated between those boundary points. And that's why the open methods is much more it seems at initially that open methods are much more reliable and easier than the bracketing methods, but there is a loophole. The open methods does not ensure to converge to a root. Since there is no boundary and there is a single bounding point, and there is a single point, the initial point, there is no assurance that you will converge to a root. So in bracketing methods it was ensured, but in open methods it is not ensured that you will find the root, and that's why it is much more riskier than the bracketing methods, but open methods are much faster than the bracketing methods. So among the open methods, so we will first cover the simple fixed point iteration method. So let's see the details of how we can apply this method for a specific problem. So any function, say for example in the last few slides, in the examples we had used a function like f of x equal to x square plus 2x plus 3. So any function can be rewritten in this form, x equal to g of x. It is a special kind of form of which can be proved from any kind of function. So this is the first step of simple fixed point iteration, that we specify a function into this new form of equation 1, x equal to g of x. So what is the benefit of that? So through equation 1 we can find the new value of the root estimate using the previous one. For example, if we write this equation 1 into an iterative form, it will look something like this: xi plus 1 equal to g of x. That means from our previous iteration we would get the value xi, and then we insert that xi into this equation, and from there we get our new approximation of the root. And that's the usefulness of this simple fixed point iteration, which is simple. That's why it is called simple fixed point iteration method. So using this iterative approach, xi plus 1 equal to g of xi, we can calculate our approximated roots at each iteration with simple calculations, with simple methods. So once we calculate the our new approximation roots at each iteration, so we can calculate the approximate error percentage using this familiar formula that we have been using in the last few slides, which is defined as the new root minus the previous root divided by the new root into 100%. That's the formula. So the result of the present iteration minus the result of the previous iteration divided by the result of the present iteration. And that is the definition of approximate error percentage. So this formula is very much useful for terminating our code whenever we are applying a Python code or MATLAB code. So these criteria are very much useful. So that's why in the previous few methods, that means the bisection methods or false position methods, we have used a pre-specified tolerance limit epsilon. So that is similarly we are going to use that same method in these simple fixed point iteration. Even actually these type of epsilon a, that is the percentage approximate relative error, this is going to be used in almost all of our numerical methods, because that is a simple procedure to terminate our code, and that's why we are going to use this formula in almost all of the numerical methods that we are going to cover in these numerical methods course. So what we are going to do, we are going to just calculate epsilon a, the approximate percent relative error, and we are going to just check out whether this relative error is less than a pre-specified tolerance limit epsilon s. If it is lower than this epsilon s, then we are going to terminate our code, and if it is not, then we are going to use further iterations. So that's what we have been using in our last few slides. So let's look at the detailed algorithm of simple fixed point iteration. In step 1, we are going to rewrite our function value f of x in a specific form, x equal to g of x. That is very simple method. And then we are going to transform this equation 1 into the iterative form, which looks like this: xi plus 1 equal to g of xi. So equation 2 is going to be used in the later steps. So that is our first step and our second step. In the third step, we need to calculate the relative percentage error using the two previous approximations of them. That means xi plus 1 and xi. So using these values, we can calculate the epsilon a, and in step 4, we are going to check whether this approximate percentage error is less than a previous pre-specified limit or not. If it is less than the limit, then we are going to terminate the calculation, and if it is not, then we are going back to equation 2 and recalculate the whole procedure. So these are the steps of simple fixed point iteration algorithm. That is very much straightforward. So let's look at an example that we are going to use in this slide, and I hope after this example you will find the method more easier to understand. Say for example, we are given a function f of x equal to e to the power minus x minus x. So this is our function, and we need to find out the root of this function using simple fixed point iteration approach. So what we are going to do, according to step 1 of the algorithm, we are going to rewrite this function into our specific form. That is, if we want to find out the root, that means the function of f of x, which should be equal to 0. That means e to the power minus x equal to 0. Then we change the x from the right hand side to left hand side, and then we will get this equation x equal to e to the power minus x. So this is our first equation, equation 1, and we are going to write this equation into our iterative form. That means the step 2 of our algorithm, which should be look like this. That means xi plus 1 equal to e to the power minus xi. Here the I should be at the subscript of x. It's a printing mistake, I am sorry. It should be xi. I should be at the subscript. So this is our iterative formula. Okay. So we are going to use this formula in our later steps to find out our new approximations of the root. So at the first iteration, we need to specify a single initial point xi. So look at this. We need to specify a single point. In the bisection and false position methods, we had to use two specified points. Okay. But since simple fixed point iteration is an open method, open methods always require a single starting point, and that's why we are going to specify a single starting point of xi, which is 0. So it is an initial assumption. It can be anything you like. You might set it to xi equal to 5, xi equal to 100, xi equal to 20, whatever it is. But initially we have to specify a single point. So say for example we are assuming our initial base of xi to be 0. If xi equal to 0, we insert this xi equal to 0 to our iterative formula, then it becomes e to the power minus 0, which is 1. That means xi plus 1 equal to 1. So this is our first approximation of the root in the first iteration. So after the first iteration, we get our first approximation of the root, which is 1. And using this new value 1, we are going to find out our later approximation in the later iterations. So before diving into the later iterations, first calculate the error. Since our initial base was 0 and our initial base of the root is 1, that means we calculated the value 1 using this iterative formula. So this is our new approximate root. Then we can use the relative error percentage formula, which is 1 minus 0 by 1. That means new value minus previous value divided by new value, which turns out to be 1 minus 0 by 1 or 100%. So in the first iteration we got an error of 100%. So we need further iterations. Iteration 2. So upon the first iteration we got our approximated result, which is 1, and that is going to be our new xi, and that new xi is going to be used in our new formula, iterative formula. So which is e to the power minus 1, and it turns out to be 0.367879441. So this is our new approximation of the root in the second iteration. Similarly, we calculate the error percentage, which is 171.8%. Oh my god, the error has increased from 100% to 171.8%. But we have nothing to do. Let's calculate further. So after the second iteration, we have our new root, which is 0.367879441, and we are going to use it as our new xi, and we are going to implement this new xi into our iteration formula, which turns out to be 0.6922000627. And if we calculated the relative percentage error, it turns out to be 46.854%. Look at this. Now the error has become very much slow, reduced from the previous iteration. In the second iteration, the error was 171.8%, but now it is 46.854%. That's a huge reduction. So let's calculate further. In the fourth iterations, if we calculate, we will get a new approximation of the function root, and we can get the approximate error. So we are not showing the whole calculations here, rather we are showing you the table that is going to be the resultant of your hand calculation or MATLAB code. Look at this. In the first iteration we got an error of 100%, in the second iteration 171, then the error started reducing 46.9, 38.3%, 17.4%, 11.2%, 5.9, and so on. Look at this. Initially the error, although the error increased, but later the arrow started to decrease. So that's how we apply the simple fixed point iteration approach. Even in the just in the 10th iteration we got an error of only 1.11%. So in the 10th iteration our estimation gets very closer to the original value, because the only 1.11%, that means we are already very much near or closer to the original root. Okay. So we are using this value of epsilon a to terminate our code. We just specify our predefined error limit epsilon s, and we continuously compare the value of epsilon a with epsilon s. So there is an alternate graphical approach. That some of us might have used it in our previous educational career. We have seen that we want to rewrite our function in a new form, x equal to g of x. So both of these terms on the left hand side and on the right hand side. On the left hand side we have x, and on the right hand side we have g of x. So both of these terms can be considered as separate functions. For example, on the left hand side we have x, which can be denoted as function 1, f1 of x, and on the right hand side we had g of x, which can be denoted as new function f2 of x. So if we plot these two functions separately, f1 of x and f2 of x, we will get a single intersection point at this point. Look at this, at this point. And this point, intersection point, is our desired rule. Remember, the function value is not our desired rule. Rather, where the functions intersect, the corresponding x-axis location is our root. So that is an alternate approach to our simple fixed point iteration. In the last case, what we did, we draw the whole function f of x equal to the power minus x, and we have seen where the function intersects the x-axis, the root lies there. But in this case, what we do, we separate the original function into two separate functions, f1 of x and f2 of x, and we plot these two separate functions on the same graph, and we find out the corresponding x-axis location of the intersection of the two graphs, and that is our. So this is an alternate approach to our simple fixed point iteration, but the problem is that this function we have to sometimes use some more complex functions. As a result, implementing two separate functions is much more costlier than the implementing a single function. But both of them can be applied as well. So we have seen that we have already told you how the simple fixed point iteration or the open methods are different from the bisection methods or the other bracketing methods. Because the bracketing methods ensure the convergence, and bracketing methods are sometimes more reliable than the simple fixed point iterations or other open methods. But the open methods are faster than the bracketing methods. So let's see how the open methods convergence, whether some open methods ensure the convergence or not. Let's look at some of the figures. Look at this. In the first figure, there are four figures, and there are four separate functions, and we have already seen in the simple fixed point iteration, we rewrite the function in the form x equal to g of x. So in our left hand side of the equation we have x, and on the right hand side of the equation we have g of x. So if we plot these two functions separately, we will get these four separate functions. So y equal to f1 equal to x, which keeps same, which is remaining same in all of these figures. So what we are watching here, we are trying to find out if the right hand side function g of x changes, how the convergence changes. Okay, so on our left hand side, y equal to x, y equal to x, y equal to x, y equal to x. So all of in all of the figures, we compare the graph of g of x with the graph of x. Okay, so what we see in the first figure, we have a function y equal to x, which is a straight line through the center point, and we have another function g of x. Okay, we plot these two graphs, and there is an intersection point here, and we need to find these roots using simple fixed point iteration. For example, initially we guess the value x0. Okay, here the value initial point x0. So what we do, we calculate the function value g of x at this point, and similarly we calculate and this is going to be our initial point for the next iteration, and that means xi, which is this point, and at this point x1 is our corresponding the first root after the first iteration. And similarly in the second iteration we get our second root x2. So look at this, the function values gradually converges to the original root. So our iterations are very much converging for this special case. Whenever we initiate our value from x0, our function, our iterative process converges to the original root. So in this case, for the first case, we have seen that for the special form of g of x, our function converges to the original root, and that's why the figure A ensures our convergence. Okay. So this is also called a monotone pattern. That means it is gradually decreasing the error and it converges gradually to the original root. For the second case, that means figure B, we have y equal to x similar to the first case, and we have separate g of x. That means we have now a decreasing function y equal to g of x, and our original root, the true root, is at this point, the intersection of the two graphs. And if we initially assume that x0 is our initial approximation and we calculate the iterations, and we gradually converge to the original root. So this is also another convergence pattern. And but look at this, in this case the pattern is spiral. That means it gradually spirally converges to the original root. That's why this pattern, this convergence pattern, is called spiral pattern. In the first case it was monotonous pattern. That means the error gradually decreased, the pattern gradually decreased and converged to the original root. But in the second case, the figure, the method convergence to the original root show a spiral pattern. So both of these cases, figure A and figure B, ensures the convergence. But what about figure C and figure D? Look at this. In figure C, the y equal to x graph is similar to the previous two cases, and now we have a different form of g of x. Okay, a different form of g of x. So for example, if we initiate our simple fixed point iteration from the x0 point, we will see that we are gradually going further from the original root. We are gradually going further from the original root. This is not the convergence. Okay, so in these cases, the simple fixed point iteration method fails with these starting point. So what we need to do whenever our iterative process diverges, so we need to terminate our calculation and restart the calculation with a new starting point. That means we need to change the x0 point. So that is very much crucial for applying the open methods. Whenever we see that the methods are no longer converging, rather the error is increasing from iterations to iterations, we need to stop the calculation there and restart the calculation again with a new starting point. And that is what we are watching here in figure C and figure D. So figure C is a monotonous pattern because it gradually going away from the original root location. This is a monotonous pattern. That's why it is called the monotonous divergence pattern. In figure G, similarly, we have a divergence pattern, but in this case, the divergence is going in spiral pattern. That means we have a new g of x, which is this y2 equal to g of x graph, and y equal to x graph is our similar case for the last three cases. But if we start with the starting point x0, now this function diverges spiral. Okay, so in this case also convergence is not ensured, rather the pattern diverges. So in this case also simple fixed point iteration fails with this starting point. So what we need to do, as we said, we need to stop the calculation and we need to restart the procedure with a new starting point. So this is called a spirally diverging pattern. So in these four cases, we have seen four separate cases of monotonous convergence, monotonous divergence, spiral convergence, and spiral divergence. So these things can happen in simple fixed point iteration in your practical cases. So whenever you are applying the simple fixed point iteration in MATLAB code or Python code, you need to be assured that you are not diverging, because once you are starting diverging and you do not check the code from being more diverged, then it will happen that you might consume the whole memory of your computer, because the process is never converging. It becomes bigger and bigger, the error becomes larger and larger, and it becomes impossible for the method to converge anymore. And that's why we need to be very much concerned, and we need to be very much careful whenever we applying the open methods, not just simple fixed point iteration, but other open methods to find the specific truths. But how do we check for the convergence or divergence? So that means, how do we check the divergence pattern in our code? Look at these figures. Look at this figure. The convergence seems to occur only when the absolute value of the slope f2 or g of x is less than the slope of f1 of x. That means at this case in the figure 1, the convergence is assured because the slope of the function g of x, the slope of the function g of x is less than the slope of the function x. Okay, that's why in this case the convergence is assured. So what we can say, the slope of the g of x, which is termed as g prime of x, and we take the absolute value of that function, and we compare the value with 1, because the slope of y equal to x is 1. So we need to find out whether the slope of the function g of x, that means g prime of x, and we take the absolute value of the function, whether it is less than 1 or not. If it is less than 1, then our convergence is sure, and that's what is happening in figure A and figure B. In both of these figures, g prime of x with absolute value is less than 1. Okay, but in the second two cases, that means figure C and figure D, the convergence is not assured because the absolute value of the slope of the curve g of x is greater than the absolute value of the slope of the curve y equal to x. So these conditions must be specified whether the convergence, to check whether the convergence is assured or not. So in the code, if we calculate this value g prime of x and we compare this value with 1, and if we see that this value is greater than 1, then there is no assurance that there is to be convergence. That means we terminate the code there and we start the calculation with a new value x naught. Okay, but if g prime of x modulus is less than 1, it is assured, then we can say that our method is going to converge. Okay. So what we are going to do, at each iteration we are going to find a new point xi, and then we are going to find g prime of xi, then we are going to take the absolute value and we compare with the result 1. So that's how we compare the convergence and divergence pattern. So what we have learned in this lesson, we have seen the simple fixed point iteration. How do we calculate the root of a equation using the simple fixed point iteration, our very first open methods. We have also seen the difference between the open methods and bracketing methods as well. We have seen the bracketing methods require 2 starting points, but in open methods require single starting point, and that's the main difference of open methods and bracketing methods. But there are some limitations and advantages of both approaches. Bracketing methods ensure the convergence, but the open methods does not ensure that. But also open methods are much faster than the bracketing methods. So all of them have their own limitations and advantages. So what we are going to do, you please try out the MATLAB code that I have attached with this lesson to implement the simple fixed point iteration. Try to understand the code, how the error is being propagated, how the convergence is assured, and the divergence is checked out. So all of these things are to be specified in the MATLAB code. So please try out the MATLAB code at no time. So in the next lesson, we are going to try out a further improved method, which is the Newton-Raphson method, which is also an open method. So till then, thank you so much.